everyone. We will continue our lecture for today. Just to recap what we have done the last Monday, I've already introduced you, already explained how to actually derive the design equation for the three main reactors that we use to design in this course. So the first one, last Monday, I already teach you how to derive the equation for batch reactor. Then today I will continue with PFR and CSTR. However, do bear in mind, you're not required to actually memorize or to actually, to know in detail, as I will not test you on the derivation. So derivation part, you will not be tested in any of the assessment. But of course, it's always good if you understand how the equations are derived. So later, after I finish on the derivation, then we will start learning how to actually apply the equations to solve the application. Means how we use to apply the equation to solve problems related to the design of reactor. So the derivation is a bit dry because it's more of theory, more of connecting the mathematics to the chemical engineering scenario. So it can be a little bit dry, but as I said, it's better if you actually understand how the equations are derived. Okay. So last Monday, batch reactor. Today we will concentrate on the two flow reactors, CSTR as well as PFR. Okay. So in this slide, it's shown how do we derive the equation for CSTR. So if you remember last Monday when we derived batch reactor, the equations are a little bit complicated because it's an integral equation. If you remember, kalau batch reactor, design equation dia is in the form of an integral equation where it is for batch reactor, we will always talk about finding the reaction time. Okay. However, when we talk about flow reactors, the design equation is more towards finding the volume of the reactors. Okay. So you will see for both PFR, CSTR, design equation here is in the form of volume of the reactor, meaning we want to find the volume of the reactor. Then for CSTR is definitely way easier compared to batch, and later you will learn for PFR. Okay, why do I say it's easier to derive? Okay, first of all, you still will start with the general mole balance or design equation for the reactors. Always start with the same general balance equation, which says that molar inlet molar flow rate FA0 minus outlet molar flow rate plus rate of generation in the reactor equals to rate of accumulation. Okay, yang ni kita dah belajar daripada chapter 1. The other day also I already taught you this. Okay, but as I said, equation ni will have to be tweaked or modified according to the properties of the reactor. So when this reactor has this property, equation ni pun akan berubah accordingly. So we have to understand what is the reactor property and how it affects the design equation. So first property of a flow reactor, okay, we are talking about CSTR, continuous stir tank reactor, is that since dia ada outflow dengan inflow, because it's an open system, right? Flow in, flow out, there will be no accumulation of A in the system. Okay, sebab A will not be accumulated because after certain residence time, A will have to flow out. So we flow in A after certain residence time, A will have to be flown out. Okay, because there's no accumulation due to the inflow and outflow, hence the rate of accumulation yang DNA per dt tu becomes zero. Okay, so kalau batch ada accumulation sebab batch closed system, it will accumulate. Flow because dia tak ada dia ada inflow outflow and open system, hence rate of accumulation to become zero. DNA per dt is zero. Okay, second characteristics, CSTR similarly to batch reactor, dia ada stirrer. Okay, remember I told you kalau dia ada stirrer, they will ensure the concentration and temperature is concentration and heat is well distributed across the reactor volume. So this is very important because rate of reaction is influenced by concentration and temperature. So if all the volume in the reactor has constant temperature, constant heat, which is temperature, Hence, RAdV becomes RAV. Okay, means there's no more variation in the rate of reaction throughout the reactor volume. So integral RAdV becomes RAV. Okay. So now what happens to the equation? So delta per dt dah 0, RAdV becomes RAV. So when we apply this to the original equation, okay, you will see FA naught masih ada because dia ada inflow kan. Flow system, we always have inflow. So FA naught maintain. FA also have, because we have inflow, we have outflow. So FA pun ada. Ikut plus with RAdV becomes RAV equals to DNA per dt dah kosong as I explained. So become equal to 0. So equation 4, you will have to rearrange. We will rearrange the equation. Why? Because first, design reactor ni untuk flow system, we want to find volume. So volume will become on the left-hand side on its own. So the rest, you will move to the right-hand side. Okay, and then you realize one thing, as similar to the batch reactor, because we evaluate rate of reaction in terms of rate of disappearance of A. Remember I taught you rate of reaction ni based on rate of disappearance of A. So that's why it become FA naught minus FA per minus RA. So done. So we have derived the equation for CSTR. So in these three reactors yang I will teach you, okay, the other day batch, today PFR, CSTR. CSTR has the easiest equation sebab dia just linear equation, kamu boleh solve terus. Yang jadi kompleks is previously batch sebab dia integral, and lepas ni PFR pun kompleks sebab dia adalah integral. So integral tu kita kena belajar how to solve integral equation, but it's not that difficult pun lah if we understand how. Okay, so we have already derived and know how to obtain the reactor volume. So I will always put subscript V, subscript as CSTR to indicate volume of CSTR to achieve a conversion X in a CSTR. So conversion tu again merujuk kepada conversion of your reactant A, your main reactant, or I always say the limiting reactant. Okay, so the bigger the reactor, the more time it will take the reactants to flow completely through the reactor, and thus more time to react. So volume reactor will also influence your reaction inside it. Okay, so later you will learn macam mana volume ni mempengaruhi the rate of reaction as well. Okay, then now next part is a little bit of understanding the equation. Okay, equation 2 previously, as I just derived, is FA naught minus FA per minus RA kan. So FA naught inlet molar flow rate, FA outlet molar flow rate, minus RA rate of disappearance of E. Okay, but again, as I taught you last Monday, equation ni mesti ada conversion because we will always measure the reaction punya performance through conversion. Okay, so the equation has to introduce the conversion into the equation. So kamu tengok equation yang tadi saya derive, we still don't have yet conversion. But we have learned last Monday. Yang there is a correlation. Okay, we know that from the conversion punya equation, conversion X equals to FA naught minus FA per FA naught. So kalau kamu lupa conversion tu senang je. Conversion equals to in minus out divided by in. So kalau in terms of molar flow rate, FA naught in minus out FA divided by in again FA naught. Or if I rearrange the equation, akan dapat dalam bentuk FA equals to FA naught minus FA naught X. Okay. In this week, if you are still confused about this, it's very fine. As I told you, as you go many weeks after this, you will keep looking at the same thing. Automatically kamu akan ingat. Dalam this week, kalau kamu rasa macam banyak sangat, equation is very normal sebab kamu tak familiar lagi. Tapi that's the advantage of reaction. You will keep using it, that eventually you akan ingat. Okay, so we already correlate FA as FA naught minus FA naught X. So you see now, from this correlation, from this conversion correlation, I already have X. So what I do, I replace my FA, or the original one, with FA naught minus FA naught X. So when I do this, okay, now I will get volume CSTR equals to FA0 X. Kamu tengok mathematics kan, FA0 tolak FA0 become 0. FA0 minus minus become positive. So FA0 FA0 plus FA0 minus FA0. Betul lah, FA0 minus FA0 0. Then minus minus plus you get FA0 X. FA0 dah habis. Kita dah keluarkan FA0, no more FA0. Remains with FA0 X per minus RE. So now your equation has an X. Tadi equation yang kita derive awal tu tak ada X. Now the new one has X. However, part ni yang a little bit confused. Sebab tu reaction dia, as I always tell you, dia susah. I have to prepare you to it is because, okay, in this case, equation ni kita dah derive. However, equation ni only valid to certain condition, or in this case, this equation is only valid if you are calculating the volume of one reactor only, one CSTR. On the other hand, remember I taught you CSTR, PFR, we can actually use it more than one reactor connected in series. Okay, dalam case katakan kita guna more than one reactor connected in series, kita nak cari volume dia. Let's say I want to find the volume of the second reactor, third reactor ke, fourth reactor in the series. This equation is no longer valid. Okay, but don't worry. In this chapter later, I will teach you reactor in series. Then kamu akan faham how this equation akan berubah when I calculate for reactors in series. On this stage, at this stage, we just remember equation ni untuk find the volume of CSTR, but only if it's for the one reactor. Means kita nanti tindak balas you tu, if your reaction only uses one reactor, this equation is valid. But if you use more than one reactor in series and you want to find the volume, this equation is no longer valid, but I will explain to you why later. Okay, right. So we are done with CSTR. Now we go to the last reactor that we will learn to derive, PFR. So PFR is the hardest one to derive. So I will try my best, but if you don't understand, it's very fine. As long as you will learn later how to apply the equation. Okay. For PFR pula, you must remember PFR ni they have no stirrer. Kan remember PFR is just a cylindrical pipe. Normally to save space they will call the pipe. So dalam pipe tu, right, imagine one pipe, the reactor will travel across the pipe. So the further it travel, more reactant will be converted. Okay. So naturally, you know that PFR tak ada stirrer. Okay, one thing, PFR confirm tak ada stirrer. Okay. Second, you imagine the reactant will travel across the pipe, right? So when it travel across the pipe, the further it goes, of course, more of your reactant will be converted. So katakan daripada permulaan reaktor tu ataupun permulaan reaktor in comparison to the middle of the reactor, in comparison to the end of reactor, definitely the concentration will not be the same because the further it travel or the longer the longer the reactor stays, must travel across, definitely lebih banyak akan converted. So of course concentration dah tak sama. When concentration is no longer the same, the rate of reaction pun definitely no longer the same. Means rate of reaction at the beginning of the reactor, at the middle, at the end, the rate of reaction is no longer the same. So we can say there is a spatial variation of the reactor, the spatial variation in the reaction rate. So tadi yang integral RAdV tu kita tak boleh jadikan RAV sebab dia hanya boleh jadi RAV bila dia ada stirrer. Tak ada stirrer, kadang tindak balas dah tak sama untuk setiap tempat dalam reaktor tu. Therefore, the integral RAdV stays for PFR. Okay, so now we understand that part already. Let us derive untuk plug flow reactor. So for those who forget, plug flow reactor, one long cylindrical pipe which can be coiled and the reactant travel across the pipe. Okay, so the mole balance equation is still the same. We always start with the general mole balance. So in minus out plus generation equals to accumulation. Okay, so first of all, similarly to CSTR, PFR always is an open system, means there's always inflow, outflow. So therefore, similar to CSTR, no accumulation. Nothing is accumulated because everything will be flown in, flown out, flow in, flow out, open system. So DNA per dt, 0. Okay, so on the right hand side now, my DNA per dt become 0. Okay. The integral RADV have to be there dan tak boleh jadi RAV sebab as I told you, concentration berubah throughout the reactor volume. Kalau concentration berubah, rate of reaction pun berubah. So there is a variation in the rate of reaction with the reactor volume. Okay. So part ni sekarang jadi susah. Okay. Kita nak musnah in the integral part, we have the RADV, integral RADV, right? So we want to eliminate this integral first. Okay, kenapa kita nak eliminate integral ni? Sebab later kita nak introduce X. When you have this integral, it's a bit hard for you to introduce the X into the equation. So can you imagine when someone, I cannot remember who derived this equation, tapi kamu bayangkan dia dah boleh fikir, I'm sure this is a mathematician, but this mathematician and I'm sure there's another chemist or chemical engineer who has to explain how this chemical engineering scenario correlates to the mathematics. So this RADV, the integral, has to be eliminated. So how do you eliminate? You differentiate all the variables in the equation. So meaning untuk memusnahkan RADV ni, saya akan bezakan FA0 towards V and FA towards V as well. Okay, so dan kita kena faham pula, if this FA0, saya bezakan terhadap V. Okay, so sebab dia DV kan, so dia kena bezakan terhadap V. Dan kamu kena faham pula, okay, mathematician will have to refer to a chemical engineer to explain, adakah FA0 berubah dengan reactor volume? Okay, then you have to understand pula, FA0 tu molar flow rate yang masuk. Okay, so regardless reactor punya volume tu panjang ke pendek ke, how long or how short, or how it shapes or it forms, inlet molar flow rate tu tetap sama. Means if I prepare 10 mole per minute, 10 mole per minute sahajalah molar flow rate dia. So the chemical engineers will explain that the inlet molar flow rate doesn't change with the reactor volume. Sebab that's the fresh feed yang you prepared to enter the reactor. So dFA0 per dV is now become 0. Okay, sebab there is no changes in the inlet molar flow rate with the volume of the reactor. So become 0. Next one, FA pula. So the next one dia kata, okay, kita kena bezakan outlet FA ni tak semestinya outlet molar flow rate. Molar flow rate at any time during the reaction or after the reaction. So the question we ask, what about the molar flow rate, outlet molar flow rate ni pula? Outlet molar flow rate dengan volume. Okay, FA ni dengan volume. Okay, so then a chemical engineer will explain FA ni molar flow rate anytime during the reaction and after the reaction. So as I told you, molar flow A ni as it travel inside the reactor, you travel to the next length, dia akan berubah dah sebab A will be consumed as it travel across the reactor. So FA akan berubah dengan reactor volume. FA, the molar flow rate, outlet molar flow rate will change with the reactor volume, or more specific, will change as it travel across the reactor. So then chemical engineer will inform the mathematician, dFA per dV ni ada. So it become minus dFA per dV. FA0 beza terhadap V jadi kosong, minus FA per dV, we differentiate ada, minus dFA per dV, plus RADV ni bila pengamiran kita bezakan, the dV no longer there, it become RA. So now the equation become dFA per dV equals to minus RA. Okay, so now daripada equation 3 jadi equation 4. Okay, then pula, that's the part yang kadang-kadang saya rasa macam kesian jugalah chemical engineer. You really have to understand this. dFA per dV equals to minus RA ni, kalau kamu perasan satu benda yang tak cukup lagi. Why it's not enough? There's no conversion. Remember, kita always nak conversion dalam equation. No conversion, It's very hard sebab we always, kalau kita akan monitor the reaction punya performance tu mesti based on conversion. Means berapa banyak A saya tu converted jadi produk. Why? Because in a real practical situation pun kita nak tahu semua raw material kita yang masuk tu jadi produk tak. Let's say you want to produce product B. So ideally you want all A tu yang masuk tu jadi B. So always you will measure A tinggal berapa, A tinggal berapa. Sebab tahu the lesser A left means the more B is produced. Okay, so now nak kena introduce X pula. So how do we introduce X into the equation? So then come back pula, kamu tengok daripada equation number 4 ni, only one variable has connection to X, which is FA. Because we learn dah FA equals to FA naught minus FA naught X. Kita dah belajar kan equation conversion. Ini kalau saya bezakan FA towards volume, means dFA per dV, I can also differentiate FA naught dengan FA naught X ni. Bila saya differentiate, saya dapatlah dalam bentuk dFA per dV in the form of X. So what I do is I will differentiate FA towards V. So become dFA per dV on the left hand side, and I differentiate on the right hand side as well. So then when I differentiate right hand side, okay, kena fikir pula. Okay, when kita differentiate FA naught towards volume, okay, so bila dV lah kan, so become dFA naught per dV. Okay, so matematik kata bila kita bezakan, it become dFA naught per dV. But then a chemical engineer will have to then explain again, macam saya kata. Tapi FA naught tu inlet molar flow rate. Inlet molar flow rate, tak kisah how the volume of the reactor looks like, the inlet molar flow rate is what I prepared initially. Okay, so it doesn't change with the reactor volume. So dFA naught per dV become 0, tak ada. Okay. Next pula, we have to differentiate FA naught X. So kalau mathematics, if you have learned mathematics, remember, when I want to differentiate two variables, I differentiate the first variable, multiply with the second one, plus differentiate the second one, multiply with the first one. Meaning, I will have to differentiate FA naught towards V, multiply with X, plus I differentiate X towards V, multiply with FA naught. Okay, so the first one, when I differentiate FA naught towards V, sama conclusion dia kosong. So 0 multiply with X, you get 0. So tak ada juga. Okay, the second one, we will differentiate X towards V. So dx per dV. So again, chemical engineer will then to explain. Conversion berubah tak dengan reactor volume? Of course, because as I told you, the further the reactor travel in the reactor, okay, inside the reactor, the longer it travel, the more the conversion will increase. Sebab more A is consumed, conversion will increase. So means there is a changes in the conversion with the reactor volume. So dx per dV tu ada. Then multiply with the first variable FA naught. So now dFA per dV equals to minus FA naught dx per dV. So see tadi dalam equation 4 dFA per dV. Sebab saya kata we said that we need conversion. So now dFA per dV becomes minus FA naught dx per dV. So now what I do, I combine equation 4, equation 6. So meaning minus FA naught dx per dV equals to minus RA. So it combines 4 and 6, and again the minus RA RA tu kena jadi minus. So kita akan pindahkan the sign, the negative sign to the other side so that I get in terms of minus RA. So now become FA naught dx per dV equals to minus RA. Okay. Then what I do with this equation tak habis lagi. Okay, sebab kita design reactor, kita nak cari volume kan. We always want to find, for flow reactor ni senang je kami ingat. Flow reactor kita nak cari volume dia. Volume CSTR, volume PFR. So meaning equation 7 ni, kita akan rearrange balik and kita akan integrate. Sebab kita nak dalam bentuk integral. Integral is easier to solve in comparison to differential equation. So when you rearrange and you integrate, finally you get the final design equation. Yang saya tadi ajar bahawa banyak derivation ni sebenarnya nak kita sampai kepada this final design equation. So, volume PFR, tadi kita volume CSTR kan, ni volume PFR equals to FA0, inlet molar flow rate, integration from 0 to X. So daripada 0 to X ni pun kamu kena betul-betul faham. Kenapa kita integrate daripada 0 to X is that, again, dia ada limitation dia. This equation is when you have one reactor only. Single reactor macam CSTR tadi. Sebab single CSTR, kita akan integrate from 0, means no conversion. Initially bila reactor baru masuk tak ada conversion kan, daripada 0, no conversion towards X, the final conversion or the desired conversion, dx per minus RE. So this equation pun sama macam CSTR, akan ada limitation, is only for single CSTR. Tadi untuk single PFR. So next week I will teach you why this equation will change when we are doing it for reactors in series. Okay, kalau reaktor tu dah bersiri, kita nak kira volume reaktor kedua, reaktor ketiga, equation ni dah kena or dah tak valid, or in more simpler words, it has to be modified accordingly for that situation. Okay, but for now, for at the meantime, okay, sebab saya baru ajar satu reaktor, we stick with this equation, means volume PFR, FA0, integration from 0 to X, dx per minus RA. Okay, so done on deriving the equation. Okay, then now we come to the part where we learn how to apply the equation. Okay, so dalam chapter seterusnya, chapter 2 lepas ni, sekarang yang saya akan ajar, chapter 3, chapter 4, chapter 5, chapter 6, kamu akan tengok balik equation ni. Tapi equation ni kamu akan tengok dia akan bertukar, dia akan modify, it change according to the reaction. Okay, so now I will start teaching you how do we apply these two equation. With the idea kita nak cari volume CSTR, volume PFR. Batch kita tak sentuh lagi. Okay, batch nanti kita sentuh kemudian. Sekarang kita cakap pasal CSTR, PFR dulu, flow system. Okay, now you have in this, kamu kena imagine senario ni dahulu. Okay, alright. So let's say you imagine you are working on a, let's say you're working in a plant. Okay, let's say your company decided to use a new types of reaction. Okay, let's say sebelum ni produk ni dihasilkan melalui method A, reaction A. Okay, somewhere in the laboratory, all the chemical, usually the big chemical plant, they have R&D sendiri tau. They have R&D sendiri, they ada their own chemists working in the R&D lab. Okay, so let's say this chemist has already find a new method to produce this product. Okay, a new method ni menggunakan reaction yang baru, means entirely new reaction that nobody has done before. Okay, so this chemist and let's say this chemical engineer, okay, you have a chemical engineer as well. Let's say they will establish this kinetic data for you. Okay, so this kinetic data, what I mean by kinetic data, they have done from the experimental work in the lab, which actually nanti dalam lab kamu yang sebenar reaction dan dalam chapter 5, kita akan belajar benda ni. Kita akan belajar macam mana daripada eksperimen tu kita akan dapat data kinetics ni. In simple words, data kinetics ni adalah in the form of a table of which it consists of two important information, conversion and minus RA. Minus RA itu apa? Rate of reaction, right? Rate of disappearance of A. So let me repeat again. Rate of reaction ni kita pernah belajar kan? Ada rate of disappearance, rate of formation. You have learned rate of disappearance or rate of formation can be calculated for all the species. Remember? But as I told you, in the lab or usually for the reaction, we will measure in terms of minus RA, rate of disappearance of your main reactant A. So the data that is obtained from the laboratory work, which you will do later, is in the form of X and minus RA. So table ni information kan maksudnya for each of these conversion. So kamu bayangkan chemist tu, chemical engineer tu akan buat apa? Setiap reaction tu dia akan run, okay, dia akan measure conversion and dia akan measure minus RA dia. Bukan setakat measure, dia kena calculate sebenarnya. Okay, so dia akan dapat untuk every conversion ni merujuk kepada your A, conversion of your reactant A, they will also get the minus RA for each of this conversion. Okay, so from this table of data, we can actually use to calculate volume of PFR and volume of the CSTR. Okay, so meaning we can know the size of the reactor by having this information sahaja. Okay, so but then the question will be, macam mana kita nak guna information dia? Okay, so this information is in the form of a table, or we can also represent the same information in a form of what we call a plot, and this plot is called a Levenspier plot. Okay, kamu akan faham kenapa menggunakan plot is sometimes easier compared to menggunakan using the table. So the information yang X and minus RA can be in the form of a table as has shown in this slide, or we can use the table to plot the Levenspier plot. But you kena faham, kalau table, the data is X minus RA. Kalau kita plot Levenspier plot, it's X for the X-axis. The Y-axis is 1 per minus RA. Okay, so sometimes student confused kalau table X minus RA. Tapi kalau kita plot Levenspier plot, dia mesti 1 per minus RA. Nanti kamu akan faham kenapa. Dia mesti ada reason kan. Mungkin tak sebarangan. Kenapa plot ni mesti 1 per minus RA? Minus RA kan lagi senang. That is the reason. Okay. But the keyword plot dia mesti 1 per minus RA versus X. So imagine, katakan kamu dapat data tu dalam bentuk table. You can use the table. Tak salah pun. Tapi you can also convert it into a plot. So when you plot it as 1 per minus RA lawan X, it become Levenspier plot. Okay, so we can use either one alternative of the data representative to calculate the volume. Guna table pun boleh, guna plot pun boleh. Okay. Now, kenapa guna plot tu? Saya kata guna plot lebih senang. Kenapa guna plot lebih senang? Sebab from the plot, you can actually visualize how to calculate the volume. What do I mean by that? Okay, right. Kamu ingat kan, kita nak cari volume CSTR. Kita start dengan CSTR dahulu. Volume CSTR tu, dia punya formula kalau single CSTR, I'm still talking about one CSTR, means kita hanya satu CSTR to run the reaction. Formula dia kan FA0 multiply with X multiply with minus RA. Dia jadi, multiply with 1 per minus RA ataupun FA0 X per minus RA. Ni equation dia kan. Okay. When I plot this Levenspier plot, okay, kamu imagine Levenspier plot dia 1 per minus RA lawan X. Do you realize, okay, let's say contohnya conversion reactor saya tu 80%, 0.8. Okay, so conversion dia 0.8. Kita nak tahu berapa volume reactor kalau conversion dia 0.8. So when I plot the graph, if you realize, okay, the volume of the CSTR is actually equal to the area of the rectangle of this Levenspier plot, or in simpler words, the area of above and below the curve of the Levenspier plot. So kalau kamu tak faham, okay, kita tengok kamu bayangkan segi empat yang merah ni, okay, mestilah kita imagine conversion dia 0.8. So kita nak kira volume of the CSTR, saya kata volume CSTR ni sama dengan luas kotak merah ni. Okay. Kalau kita nak kira luas kotak merah ni sama dengan apa? Sisi darab sisi kan, panjang darab lebar kan. So dia punya lebar is X kan, conversion X. Dia punya panjang adalah apa? 1 per minus RA. So kamu perasan X multiply with 1 per minus RA multiply with FA0, you get the volume. So sebenarnya volume CSTR adalah sama dengan area above and below the curve multiply with FA0. Sebab tu saya kata kenapa sometimes they use Levenspier plot, sebab dia boleh imagine dengan lebih senang. Means kalau saya cari volume reactor ni, saya darab je 0.8 dengan 1 per minus RA ni, katakan 10. So 10 multiply with 0.8 multiply with FA0. Jangan lupa sebab dalam equation ada FA0. Let's say FA0 dia 10 mole per second. Dan kamu dah dapat volume dia. So that's why we use CSTR, the Pelvis wave plot, because it's easier to imagine the volume through the curve punya area. Okay. Okay, let's say you tak faham lagi, is okay. Let me give you a simple example first. Okay. So, katakan example ni kita guna dulu table. Okay, kita guna table, kita guna plot, kita nak cari volume reactor. Okay. So, let me teach you using the table first. Right. So, kamu kena ingat, bila kita nak solve problem ni, okay, we always remember dia mesti bagi kita table, conversion minus RE. Kalau table tak ada information ni, you cannot use to find the volume of the CSTR. Okay, so dia kata dalam soalan ni, reaction carry out in CSTR, reactant A enter reactor, rate dia 0.4 mole per second. Okay, dan dia kata kira volume to achieve 80% conversion in a CSTR using the table. Okay, so first information, apa yang kita tahu, dia kata enters reactor, rate of 0.4 mole per second. So I already taught you a little bit, but again you have to understand. Okay, when you see a number, kita nak tahu nombor tu apa, kita tengok unit. From the unit, you know dimension, you can guess the symbol. So mole per second, dimension dia mole per time. Mole per time tu mesti apa? Rate, right? Something per time mesti rate. So rate apa? This is mole, right? So molar flow rate. Tapi molar flow rate, kamu tahu F, right? So this is F. Dia mesti berkaitan dengan molar flow rate. Tapi molar flow rate ada in dengan out. Kita tahu ni molar flow rate A. Dia boleh jadi Fe0, dia boleh jadi Fe. But the question says enter reactor. So maksudnya apa? Fa0 means molar flow rate yang masuk ke reaktor. Means molar flow rate tu belum lagi tindak balas berlaku. So Fa0 0.4. Okay, so kita kira volume kalau conversion dia 80%. Okay, so before you forget, nak memahami table ni maksudnya bila conversion 0 minus RA dia 0.45. Bila conversion dia 0.1 minus RE dia 0.44. So on and so forth. Okay, jangan lupa conversion ni dalam bentuk fraction. So as I told you, sometimes conversion dia bagi dalam bentuk peratus, sometimes dia bagi dalam bentuk fraction. But remember, kalau beri in form of percentage, please convert into fraction. Pengiraan mesti berdasarkan fraction, cannot be based on the percentage. So maksudnya, bila kita punya conversion 0.8, 80%, rate of reaction dia minus RA dia 0.10. Okay. So macam mana kita nak guna ni untuk solve? Okay. So as I told you, bila kamu nak solve, cara yang paling selamat, kita letak dulu information tu. We list down the information first. So the first information, we know Fa0 0.4. Okay, mole per second. Second information, dia kata conversion 80%, 0.8. And from the table, when X is 0.8, my minus RA is 0.10. Okay, so rate of reaction ni bergantung kepada conversion. So table ni dah bagi kamu dia punya relationship tu. When my X 0.8, my minus RA 0.10. So when you have this information, nak cari volume. So volume CSTR equals to Fa0, which is 0.4 mole per second. X 0.8. Don't forget, saya selalu ingatkan kamu, bukan sebab saya suka ingat. No, bukanlah saya kata apa. I always remind you sebab the things that I remind is the one that usually student akan make this mistake. So I have to keep remind supaya kamu asyik ingat sampai kamu tak buat salah tu. Sebab I teach, as I told you, I teach many semesters. Student tend to get confused in this. Bukanlah confused. I can understand when you have many courses, you got so many things to memorize. I understand it's not possible to memorize everything. So the only choice I have to keep remind you sampai kamu dah tahu dalam otak kamu, tak boleh buat ni. Okay, so remember again, X2 in terms of fraction 0.8 divided by minus RA. Kalau kamu confused, minus RA tu bergantung kepada X. Meaning kalau X saya 0.8, the minus RA is when my X is 0.8. So from the table, when my X 0.8 minus RA 0.10. So we calculate this, you will get, again as I taught you, right? Kita boleh guna pembatalan unit to check whether the calculation is right or wrong. Okay, so molar flow rate dia mole per second. Conversion tak ada unit sebab dia bentuk fraction, dia tak ada unit, right? Minus RA dia kan saya dah ajarkan minus RA mesti concentration per time. Or in this table is given as mole per dm cube second. Okay, dalam table dah bagi unit. So kamu akan tengok, kamu batalkan unit mole, kamu batalkan unit second, you are left with this dm cube. Dia A per B per C, C naik ke atas, it become dm cube will goes to up, become dm cube, the number. So again, kalau kamu dah dapat jawapan ni, kamu check balik. Kita nak cari volume. Okay, nak cari volume, saya dapat dm cube. Dm cube tu kan volume. So most likely your answer is right. So let's say kalau kamu tengok, kamu dapat jawapan kamu tiba-tiba second. Kamu tahu salah sebab volume mesti unit volume. So kamu check balik, mungkin equation kamu tersalah ke, yang bawah naik atas ke, atas naik bawah ke. So that's a way for you to check. If your unit is right, most likely your calculation is correct or the formula is correct. Okay, done. Now, guna plot pula to solve the same question but using the plot. So kamu imagine kamu tak ada table tu tadi, kamu diberi dalam bentuk plot, tapi kita masih nak cari volume CSTR. So soalan information semua sama. Molar flow rate masih 0.4, FA0 0.4, conversion masih 0.8, tapi dia suruh guna table ni untuk cari, dia suruh guna plot ni untuk cari volume. Okay, so how do we do that? Okay, so when you have the plot, okay, as I told you, volume dia sama dengan molar flow rate FA0 multiply with the area above and below the curve. Apa maksud dia? Okay, so kita tahu nak cari pada conversion 0.8. So you make a box of this 0.8. So dia akan ada satu kotak merah ni. Kamu cari je luas kotak ni. Okay, so meaning it will become volume CSTR FA0 0.4 mole per second multiply with the area 0.8 multiply with, this is the panjang dia, lebar dia 10. So 0.8 multiply with 10, you will get the volume as 3.2 dm cube. So part ni sometimes student akan get confused. Kenapa saya masih confused? Tadi kalau kita guna table, dia per minus RA kan. So kamu bahagi dengan 0.10 sebab daripada table kata pada 0.8 minus RA dia 0.10. However, kamu kena ingat level sphere plot dia punya yang y-axis tu 1 per minus RA. Meaning kamu darab terus 1 per minus RA tu. Kamu dah tak bahagi dengan nilai dia. Sebab ingat tak formula dia FA0X per minus RA. So FA0 multiply with X multiply with actually 1 per minus RA. So daripada plot kamu tu, kamu dah dapat straight 1 per minus RA tu sebagai 10, 10. So that's why we multiply directly with 10, you will get the volume the same. Okay, so apa yang saya nak sampaikan, student kadang-kadang confused kalau nak cari guna table tu X minus RA. Level sphere plot is X and 1 per minus RA. So when it's 1 per minus RA, you directly multiply with the value. When it's minus RA, you divide by the value. Okay, I hope you understand. Tapi kalau confused juga tak apa. Next week we will start tutorial. So tutorial kita akan buat lagi soalan. Hopefully you will understand better on this. Okay, right. So next one is PFR. Kita sempat lagi. PFR pun we can use either one, either table or the level sphere plot to find the volume. Okay, so sama je macam CSTR, PFR pun boleh. Kita boleh cari volume of the PFR using table or using the level sphere plot. However, there a bit complication sedikit. Okay, kenapa complication? Sebab sekarang tadi bila CSTR, volume reactor dia equals to FA0 multiply with area above and below the curve, which is a rectangle, segi 4. However, in the case of a PFR, kalau kamu tengok dia punya equation dia, volume PFR equals to FA0 integration 0x dx minus RA per minus RA. Or in the form of level sphere plot, the area of the volume of the PFR is the area under the curve. Kalau tadi CSTR area above and below the curve, rectangle. Tapi kalau PFR dia hanya area below the curve. So kamu boleh bayangkan kita nak kira area below the curve ni dah tak straightforward kan. Tadi segi 4 kira je lebar, darat panjang dan darat FA0 dapat dah volume. Tapi untuk PFR dia adalah area under the curve. So if you remember your mathematics back, when you have a plot with area under the curve, to calculate this, okay, kalau guna manually susah lah kan. Okay, that's why we have what we call as Simpson's rule. I hope you still remember Simpson's rule. Okay, Simpson's rule can be used to calculate the area under the curve. However, Simpson rule ni kalau kamu ingat ada banyak jenis, right? We have Simpson 1/3 rule, 3/8 rule, 5/7 rule, 7/12 rule. Okay, so you might be wonder kenapa banyak sangat rule? Kan kalau kamu ingat mathematics, dia depends on the assumption that you make when you calculate the volume. Okay. But to make your life easier, and also not to make your life easier, to make everybody life easier, it is found that the volume of the reactor of the PFR, which is area below the curve, can be calculated accurately using Simpson 1/3 rule sahaja. Okay, we don't need to use 3/8, 3/8 no. 3/8, 5/7, 7/12 kot saya rasa. Okay, we only use 1/3 rule untuk kira area under the curve. Tapi kamu kena faham macam mana nak menggunakan Simpson 1/3 rule. Okay. First of all, why is it called as 1/3 rule? It's because they are dividing into 3 points. Kamu kena faham key dia sekarang, kita divide jadi 3 point. Apa maksud 3 point? Okay. Kamu dah kena faham equation pula. Okay. Equation volume PFR ni kan untuk satu reaktor dia akan convert daripada zero, no conversion to your final conversion. Katakan dalam contoh tadi, contoh ni 0.8, 80%. So means saya convert daripada kosong, means daripada no A converted until 80% conversion. Okay. So point pertama, your very first point mesti point zero. Point pertama daripada integral ni bermula daripada kosong, point pertama dia mesti kosong. Again, kenapa start pada kosong? Sebab integration kita assume daripada no conversion to the final conversion. At this stage mungkin kamu confused. Kenapa saya kena repeat benda ni? Sebab nanti bila kita masuk reaktor yang bersiri, dia akan bertukar. So kamu kena betul faham kenapa kita titik pertama, the very first point must be zero because my reactor is converting from zero conversion. Okay. Kan saya kata ada 3 point, right? The last point, okay, first point 0. The last point must be your final conversion. So let's say reaktor kamu nak capai conversion 80%, your final X2 0.8. Okay. So I tell you the first point, I tell you the last point, right? Tapi kena 3 point kan? Okay, the third point, or the second point lah, first point, last point is the final conversion. The second point is the middle conversion, middle point between your first and your final. Or in this case, the point refers to conversion. Meaning nak kata, katakan conversion kamu daripada 0 to 0.8, right? First point 0, third point 0.8, middle point is 0.4, which is your conversion 0.4, middle conversion. So contohnya katakan saya tukar, katakan conversion kamu 60%, 0.6. Final conversion 0.6, meaning initial point 0, final point 0.6, middle point dia 0.3, or we can say middle conversion. So now you establish the 3 points. Okay, kenapa kena establish 3 point ni? Sebab then we will use the Simpson 1/3 rule based on this point. So this integral can be converted into the Simpson 1/3 rule. So the equation now becomes equals to FA0. FA0 masih ada sebab FA0 tu mesti ada. Multiply with now using the Simpson 1/3 rule, it become delta X per 3. I will explain later the delta X per 3. In bracket, you have now the 3 points. Sebab tu saya ajak kamu cari 3 point tu. Sebab Simpson 1/3 rule will have these 3 points. Tapi apa maksud dia? Maksud dia akan sama dengan 1 per minus RA at my initial X or at my initial point, means pada X saya yang kosong. I go to the back first. Plus, dia 3 point kan, saya pinjam back sekali. 1 per minus RA at my final conversion. Meaning kalau tadi 0.8 final conversion, ini adalah 1 per minus RA when my X is 0.8. The first point is 1 per minus RA when my X is 0. So ingat tak kita ada table tadi kan? So kamu kena tengok lah bila X saya kosong, 1 per minus RA saya berapa? Kalau kita guna plot, kalau kita guna table, kamu kena cari lah berapa minus RA saya bila X adalah kosong. Yang belakang akan jadi berapa minus RA saya bila X adalah 0.8, let's say. So the middle one akan jadi plus 4. 4 tu ada. Since one third rule dah kata number dia jadi 1, 4, 1. Don't forget the 4. Sometimes student confused. Dia lupa 4 tu. Even dalam physical exam, formula ni saya bagi. Memang I will give you the formula but you have to really remember. Yang middle tu akan ada 4 per minus RA at your middle X which you have to find by yourself. So dalam case contoh tadi saya kata 0, 0.8. My middle X is 0.4. So it become minus RA when my X is 0.4. Okay, so katakan senario contohnya katakan your final X is 0.6. So macam mana point dia? Dia akan menjadi 1 per minus RA when my X is 0. The last point will be 1 per minus RA when my X is 0.6. In the middle, 4 per minus RA when my X 0.3. So middle X tu kamu kena cari sendiri. Kamu kena tahu sendirilah middle X between initial and final. Okay. Next one, delta X. Kamu tahu daripada mathematics, delta tu means difference, right? Or changes. Difference. I normally use different. Difference. Apa difference tu? Okay, delta X ni merujuk kepada, refers to the gap. Okay, I have to really emphasize the gap between the initial X to the middle X or the middle X to the final X. Okay, either one pun kalau kamu kira betul, delta X dia kat depan ke delta X dia kat belakang pun masih sama kalau kamu kira betul. So for example, katakan your X is 0.8. So means 0, 0.4, 0.8, delta X dia akan menjadi 0.4. Let's say katakan 0.6, 0.6. So 0, 0.3, 0.6, delta X is 0.3. Okay. However, I have to keep mentioning delta X is not your middle X. In this situation, kalau kamu bermula daripada kosong, yes, your delta X will be the same as the middle X. If your first initial point tu adalah kosong, memang betul delta X sama dengan middle X. Tapi nanti kita akan belajar dalam reaktor bersiri, initial point ni dah tak start dengan kosong. Dia mungkin start dengan 0.4. So kamu bayangkan kalau katakan kes yang bersiri, you will also learn later. Kalau reaktor bersiri, katakan reaktor kedua, reaktor ketiga, initial point dia mungkin 0.4. Can you imagine kalau katakan initial dia 0.4, middle dia 0.6, final dia 0.8, delta X dia berapa? 0.2. Dia dah bukan middle point. So dalam senario single reactor ni memang betul. Delta X equal to middle point. But it will not be the same if your initial point is not 0. So that's why I keep reiterating. Delta X is the gap or the difference between initial to middle or middle to final. Regardless depan atau belakang, if you calculate correctly, delta X will be the same divided by 3. 1/3 rule sebab tu divided by 3. Okay, but let me again explain in the form of a question. Dalam form of question lebih senang untuk kamu faham. Okay, so let's say we are calculating the volume of PFR. In the case of yang sama macam tadi CSTR, kita guna flow rate masih sama 0.4 mol per second. Kita guna conversion pun sama 0.8. So tadi dah kira CSTR. Now let us calculate for PFR. Okay, so dia kata PFR tu conversion dia 80%, 0.8. So information dia FA0 0.4, X 0.8. So from the integral equation, volume PFR equals to FA0 integrating, part ni kamu kena betul-betul clear. One reactor converting from 0 to 0.8. Sebab dia kata final conversion 0.8 dx per minus RA. Okay, we will solve this using Simpson 1/3 rule. So become FA0 stays delta X per 3 in bracket 3 points. So first 1 per minus RA when my X is 0 plus 4 per minus RA at my middle point 0.4. So kalau kamu confused, you can actually do this form of a diagram. Initial point 0, final point 0.8, middle point 0.4. So become 4 per minus RA when my X is 0.4. Maksudnya minus RA apabila X saya 0.4, middle X saya. Plus with 1 per minus RA when my X is 0.8. Apabila X saya 0.8, minus RA saya berapa? Okay, so when you have this, then next is to solve it. FA naught 0.4 minus RA, delta X nak kira again, delta X is the gap between first to the middle or middle to the end point. So either way pun kamu tengok gap dia adalah 0.4. Delta X is 0.4. So delta X 0.4 divided by 3. If you wonder why 3 tu sentiasa stay. Okay, 1/3 rule dia kata is delta X divided by 3. So you just divide by 3. In bracket 1 per minus RA saya bila kosong adalah 0.45. 0.45 plus 4 per minus RA when my X is 0.4 which is 0.32 plus 1 per minus RA when my X is 0.8 which is 0.10. Okay, so when you calculate this correctly, again, try to do the unit cancellation. You will get the unit as dm cubed and the answer is 1.32. Okay, this is using table. Okay, last part, using plot. Okay, using plot ni, again, kamu dah kena faham, plot dia adalah 1 per minus RA lawan X. Okay, so how do we solve this? Minus RA dia, level sphere dia masih sama kan, is FA naught 0 to 0.8 sebab question ni pun masih conversion 0.8, alright. dx per minus RA dalam bentuk level sphere plot akan menjadi FA naught delta X per 3 in bracket 1 per minus RA when my X is 0 plus 4 per minus RA when my X is 0.4 and plus 1 per minus RA when my X is 0.8. Okay, part ni kamu tentu kena faham. Okay, FA naught 0.4, delta X sama macam yang tadi contoh tadi, masih delta X masih 0.4 divided by 3. Okay, yang ni kamu kena tengok betul-betul. 1 per minus RA when my X is 0. Daripada plot ni, when my X 0, 1 per minus RA saya adalah 2.22. So terus letak 2.22. Kamu dah tak bahagi. Tadi kalau table, kamu pasang kamu bahagi. Kenapa bahagi? Sebab table tu X minus RA. Plot ni dah terus 1 per minus RA. So nilai tu you straight away take. So from the plot is 2.22. So you take 2.22. Plus 4 per minus RA when my X is 0.4. So bila X 0.4, your 1 per minus RA is 3.13. Yang titik merah, yang merah ni, this one at 0.4 is 3.13. Okay, dalam plot ni mungkin kamu tak nampak clearly kan, tapi kalau saya bagi dalam soalan exam, saya akan tunjuk dia clearly lah. So when my X 0.4, 1 per minus RA itu adalah 3.13. So you straight away letak 3.13 but don't forget multiply with 4. So this in other words is actually 4 multiply with 1 per minus RA at 0.4. Sebab tu kamu jadi 4 multiply with 3.13. Last one, 1 per minus RA at 0.8. So when my X is 0.8, 1 per minus RA ni adalah 10, 10. So you straight away put 10. Okay, so you calculate this, you do unit cancellation, you will see that you get the same number. Actually, table tu digunakan untuk plot ni. So, when either use table or use plot, you will get actually the same volume. Tapi, you have to really understand kenapa kalau table is divide. Sebab table X minus RA. Kenapa dalam bentuk plot, you straight away take the value. Sebab dalam plot dia adalah 1 per minus RA. Okay, so I hope you understand. But if you don't understand, it's okay. We will continue this in the tutorial for next week. So for LO1, your tutorial will start on Monday 2:30, right? So Monday 2:30, LO1T1. LO1T1 is on Monday 2:30. For T2, your tutorial supposedly on Thursday, 2:30, right? Thursday, but Thursday petang tu, I have to go for my vaccination. So for T2, I will use your lab time. Your lab is on Wednesday. Lab kamu Wednesday pagi kan? So tutorial T2 saya pindah kepada waktu lab kamu hari Rabu. Your lab is from 8:30 to 11:30, but I just need 2 hours. So I give you 1 hour extra to sleep. I will start at 9:30 to 11:30. Okay, again for T1, kamu ikut timetable as usual for your tutorial. For T2, your tutorial is on Wednesday, 9:30 to 11:30. As I told in the previous class, you don't have to prepare anything. You can come to the class, just make sure you got pen, you got paper, you got calculator with you. We will do the question together. You don't have to do it beforehand because I know you got a lot of work. You're not expected to do it beforehand. We will do together during the class. I will upload the questions before the session. Okay, so again, we run out of time. Okay, I will see you next Monday. Thank you, everyone.
Thank you, Doctor.
Thank you, Doctor.